Welcome to a lesson with Dr. Powell. Let's take a look at a Mobius map on a Poset. Here's the Poset, the Hasa diagram for it, and the vertices are labeled. The same Hasa diagram with different labels, but see how they're related. Notice that 2 plus 5 is 7, meaning everything from this point downward over here, add together to give you a sum over here. Similarly, from here down, everything below, -4, 5, and 2 add together to give you 3 in that same position. 2 and everything below is just 2, okay? And then what about to get -1? Notice that -8, 5, and 2, everything below this point will give you -1. Everything below 7, including 7, that is everything added together, will give you 2. So going from sums to summands, these guys are called summands because they're pieces of the sum added together. So we'll just call these vertices the summands over here, this solution map. And we'll call this map from sums to summands, the solving map. And this solving map is a Z-module map or homomorphism, meaning it preserves Z-module structure, or you could think of it preserving vector space structure in R5. If you want to think of a linear transformation as in linear algebra. So because of that, we can represent it as a matrix. Now this first column should be the image of the first standard basis element or vector, E1. Notice how these things have zeros and ones everywhere, except for one location. Let's see, that's a 4 and a 5. Okay. Now the image of this, let's see what we're doing. We start with, we want a 1 in the bottom. Okay, thinking of this as first position, second, third, fourth, fifth as we order this. And then if we had a -1 in the solution, 1 and -1 would yield a 0, and zeros everywhere else are 5. Hence, we have this first column. For E2, so to get a 0 right here, we need a -1. To get a 0 right here, we need a -1. Notice that's the arrow going that way up, and then we need a 1 here to finish this off to make sure these guys will be zeros in the sum. That's reflected in this column. Similarly, I get the other columns with the respective solutions. This being first position, second, third, fourth, fifth, in this ordering: first, second, third, fourth, fifth. So after I do that with all of the columns, I can input these values, this tuple of 5 elements living in Z5 right here, or R5 if you will, in this order. So 2, 7, 3, 4, 5, or 2, 7, 3, -1, 2 in those positions, fourth and fifth, and we can do a matrix multiplication. So let's do that matrix multiplication and see if we get these solutions. Let's see, on the top, we end up getting a 2. That's good in the first position. Next one, -2 and 7, that's 5. Very good. Next one, we get -7 and 3. Hey, that's -4 as desired. And over here, this row and this right here, we get -7 and -1. That would be -8. That's good. And then we have 7, -3, and +1 and 2. Those cancel in just 7. So 7 as desired in the respective locations. So notice how this map, written as a matrix and multiplied to this column, gave us the desired solution of summands. Thanks for watching.